welcome to RF transceiver design course. We are discussing about the mixer design, and in last class we have seen widely used two coupler based mixer, which will help us to design a balanced mixer by and image reject mixer by using the coupler and combination of the nonlinear components. Now we will try to see the one of the widely used mixer, that is a Gilbert cell mixer, and how it evolved. So this is a Gilbert multiplier. It is also used as a multiplier, and you can also name it as a mixer. It is a precise 4-quadrant analog multiplier, and it has application in a mixer. So you can have both. We can use it as a both multiplier as well as a mixer. So you can see that it has a 4. So the biasing is not shown here, that is a tail biasing at the bottom and at the top. However, here there is how the mixing happens, that is explained. So if we see that it was Barry Gilbert, this is a very landmark paper and highly cited paper. In 1968, he has published this groundbreaking paper introducing this 4-quadrant analog multiplier. He has used the BJT. So you can see there is the NPN transistor, and by same thing we can also discuss how we can realize with the MOSFET. So here in this analysis, it is assumed that the device involves are perfectly matched, and there is a process ideal exponential characteristics and have a high beta. So common emitter current gain, which is given by the beta, it is a very high. So that we need to consider by discussing this multiplier or a mixer. Now if you apply a KVL equation, that what we will get is a VBE1 minus VBE2. So this voltage equal to VBE3 minus VBE4 equal to VBE5 minus VBE6. So all are biased such that all the base to emitter voltage, the difference is remain same. So the voltage VBE for each transistor is expressed as a we can use a VBE, which is a KT by Q ln of IB by IS. If IS is a constant, then we can write the ratio of the current IE1 by IE2. So if IE current is written as a 1 plus x by 2 into I, because it is a differential signal, and same because we are applying the Vx plus input, we consider V plus x into I by 2, and here V minus x into I by 2, because we are applying the negative voltage. This is a Vx plus. So there is a differential signal Vx plus and Vx minus. That is why here we are considering 1 plus x and 1 minus x. So the current IE, the ratio of current IE by IE2, we can write it down if we consider VBE1 minus VBE2 and VBE3 minus VBE4 or equal to VBE5 minus VBE4, and because this is a logarithmic equation, we can write it down the I1. So it is a I1 by IS divided by I2 by IS. So if IS is a constant, IE1 by I1 divided by I2 equal to I3 by I4 equal to I5 by I6, which is 1 plus x by 1 minus x. So the ratio of the current between 1 to 2, 3 to 4, 5 to 6 is given by 1 plus x, 1 minus x. Now, if we see this is a tail for both the tail, if there is a this current which is flowing through Q1 and Q2 is given by 1 minus y into I e by 2, and the current which is flowing in Q3 and Q4 which is given by 1 plus y I e by 2. So, this 1 minus y I e by 2 and 1 plus y I e by 2 is a differential current which is generated through the other voltage V y. So, here we have considered the voltage V x and V x plus and V x minus. Now, this voltage in Q1 and Q2 is generated through the V y means minus V y, and this is by a plus V y. Now, we will try to find out the current I o. So, now KCL is applied to the circuit, you will get I e 1 plus I e 2, that is a 1 minus y I e by 2. So, here I e 1 plus I e 2 1 minus y I e by 2 I e 3 and I e 4. So, here I e 3 and I e 4 it is given 1 plus y I e by 2. Now, the final expression of the transistor which is I e 1 2. So, what will happen here, that this is a this current which is here is also multiplied with this current which is a 1 plus y into 1 plus x and 1 minus y into 1 plus so x. So, 1 plus or minus x is multiplied with 1 minus y I e by 4. So, I e 1 and 2 the total current is 1 plus x plus or minus x into 1 minus y I e by 2, and I 3 and 4 we will get a 1 plus or minus x into 1 plus or 1 plus y by 4 into I e. So, what is your total current I o? So, your total current I o, it is a combination of current. So, you can see that the current from 3 and 2 are added and current from 4 and 1 are added, and the difference of this is here. So, that is 2 and 3 are added. So, same thing 2 because this is a connected at this node, 2 and 3 are added and 1 and 4 are added. So, this is I e 2 plus I e 3 minus I e 1 plus I e 4. So, if you write it down I e 1 current here and plus I e 3, what you will get minus I e 1 plus I e 3. If you normalize the output current, so normalizing the output current I o by dividing it by I e. So, if you divide it by I e, what you will get a output which is a x into y. So, our final aim is to multiply the V x and V y, and that we achieved by using this configuration. Now, here you can use the x signal as a RF signal and y signal as a LO signal, and what you will get Z, which is a, if you use a low pass filter, it is a IF signal. So, if you try to see this configuration, this configuration something look like a we can also draw differently. So, if you try to draw this Q1, Q2, then Q2 and Q4 has the same voltage. So, this is a Q4 and then Q3. So, this Q1 Q2, what is the current here? That is 1 minus y IEE by 2. This is 1 plus y IE by 2, and how it is stepped out. So, the Q3 and Q4, so there is a resistor. So, Q3 and Q2 are connected. So, you can connect this to, and Q1 and Q4 are connected. So, this Q1 and Q4 are connected, and there is a resistor between these two. This is a RO, and this is widely, because this circuit is if you try to redraw this circuit, this is you are seeing in multiple papers, and this is nothing but a Gilbert cell mixer. So, here in this is drawn something differently to explain, but however this is the same circuit that is widely used and available on the literature. So, and now you can use here one more transistor at this side and one more transistor at this side, and you can also use one more transistor to bias all. So, this is a V. So, what is this? This is a Vx. So, at Q1 there is a Vx plus, and this is Vx plus at Q1 and Q3, and this is Vx minus, and here what is coming? 1 minus y. So, this is a Vy minus, and this is a Vy plus. So, this is a complete mixer, and you can also use a Vx as a LO and Vy as a RF, and there are other application also where Y is used as a LO and Vx is used as a RF. So, this is how this Gilbert cell mixer is evolved. So, it is based on the BJT, same thing you can also use for MOSFET. So, whatever we have drawn, it is the same thing. So, what is the active mixer operation? Active mixers are based on the concept of current switching, and Gilbert multiplier, this is a rearrangement of the same. Whatever I explained how it is a rearrange Q1, Q2 and Q3, Q4, and this output current, if you get the Vx, this is how you can IO, which is equal to IEE 10 hyperbolic minus Vx by Vt. And if you are completely switching this, a square wave like signal is applied to the core transistor Vx plus and Vx minus to steer the emitter current abruptly between the device at each zero crossing. So, your I out, which is equal to IEE 10 hyperbolic minus Vx by 2 Vt. So, this is your 2 Vt, means you at least need to have an amplitude which is high to have the complete switching. So, this is how this mixer can be used. So, the emitter coupled pair IV characteristics. So, as it is shown in the figure, so illustrate an emitter coupled pair with the IV characteristics, and when your Vx is greater than 2 Vt, most of the current is rapidly switched between the device due to the sharp 10 hyperbolic transition and resulting in almost a square wave. So, that will, if we try to use the same thing what we have discussed, ideal switch, and that is applied the square wave, and what you need is your output current IO can be expressed as a series sign terms with the fundamental component being 4 by pi times the RF input modulated by the LO frequency omega LO. So, this is the IO current that we have seen 4 by pi IEE sin omega LO minus 1 by 3 sin 3 omega LO plus 1 by pi sin omega LO. There we have considered cos, here you can consider sin as well, and your emitter current consists of a DC component and small AC component. Due to the RF input voltage, what you will get is a IEE, which is a 1 minus y into IE, which is 2, which is equal to 1 minus a cos omega RFT into IE by 2. So, here in that your x is a sin and here y is your cos. If you multiply this, you will get a sin omega LOT IO current, which is multiplied with the 4 pi, and if you multiply this, it is a IF final is a means this LO, and if it is multiplied, you will get 2 by pi into your fully differential circuit. The second pair Q3 and Q4 is added to create a fully differential circuit, and this result in a characteristics of LO terms and the addition of RF input terms in the output. So, your IO by IE, that is a 4 by pi y into sin omega LO, and then what you will get is a cos omega RF minus omega LO t. So, this is called a double balance mixer, because you are applying the RF and LO differential, and the mixer is considered, that is why it is a double balance. And so, here you your LO feed through is cancelled out, and there is a RF feed through. So, there is neither LO feed through nor the RF input feed through to the output in the double balance, because you are cancelling out the common mode signal for both LO and RF. So, in practical situation, a small feed through may occur, because there is a transition, there is not a perfect transition happen. At one point of time, it acts as a differential amplifier, and it will amplify the signal for a very small duration of time, but still you will get a LO or RF feed through because it is not completely switching for the entire cycle. So, that is why there is a feed through will always be there in practical situation. So, for MOS, same thing you can realize by using a MOS Gilbert cell mixer. So, what is this? As we have seen, this will convert voltage into the current, and then this MOSFET will switch the current. So, this is many times it is called the transconductance stage. This is called as transconductance stage, it is also called a GM stage, and this is a switching stage. So, that is many times written as a SW stage, and then this resistor is converting current into voltage. You can use any component which can convert current into voltage, or you can also use a like a op amp, which will generate the which is like a OTA, operational transconductance amplifier. So, only the means current which is a output, and then later on you can use a circuit which will give you the current to voltage conversion. So, this is here it is a GM into switch. So, many times it is also called a transconductance switch GM into SW mixer. So, and this is a MOS version, and your I out IO current in this case is a 1 half mu n Cox W by L Vx into 4 Is mu Cox by WL minus Vx square. So, this is going to square the input. So, your Vx, so current steering condition, complete current steering from one device to other device occurs when your Vx which is equal to square root of 2 Is by mu Cox. So, it is a, you can consider mu n Cox W by L. You can also write root 2 into effective voltage V effective. So, the conversion gain is given by given condition 2 by pi Gm into RL, where Vx is greater than root 2 V effective, and where Gm represents the transconductance of the input pair M1 and M2 and RL is a load resistance. So, same thing whatever we have discussed for the BJT, you can use for the MOSFET or FET mixer. So, mixer function, the mixer operation can broken down into 3 function. As I told, the input voltage to current converter often implemented using a pseudo differential pair for simplicity and a balance between headroom, noise and linearity. It is a switching cord, that is a device M3 and M6 that commutes the RF current, and load is responsible for current to voltage conversion. So, we have already seen that transconductance stage, switching stage and current to voltage conversion stage. So, this is almost there in all the mixer, and the transconductance is switched by the RF, and LO means switching is done by LO, and then you will have a voltage current to voltage conversion. There is one important thing, that is your, because this is a differential signal, this is a single ended antenna, which mostly we have antenna which is a single ended, and in that case you need to have a single balance mixer. So, before that I just want to add one thing, that here in this configuration there is a constructive interference for RF and destructive for LO. That is why the LO to RF, IF fade through is a minimum in a Gilbert cell mixer, and that is why it is widely, and both RF fade through is also minimum. So, that is why it is also widely considered mixer in multiple application, but it has a one disadvantage, that it consumes more power, and it has a multiple stack transistors are there. So, and it require a differential input. So, for your antenna, if because your LNA is a single ended, now if from LNA single ended input is coming, then you need to convert into the differential in order to get the higher in order to use this Gilbert cell mixer, or otherwise you can use the input as a, means you can give the input at one side and other is a ground. So, there is a differentials the way we use in the differential amplifier, but it will have a higher noise. So, that is why there is one more configuration that is widely used, is a single balance mixer. So, in single balance mixer, that is a single ended RF input, which is so how the single balance mixer will be done. So, this is a RF input, there is a VLO plus, VLO minus, and this RF, if you consider the DC current IDC plus IRF, where IRF is given by GM into VRF, where because this is going to convert voltage into the current, and that current is nothing but GM into VGS, whatever voltage you apply here, GM into VGS, and that VGS is nothing but VRF cos omega RF t. And differential LO, you can represent differential LO as a 4 by pi cos omega LO. Same, we have used the same equation for all the square LO. Now you multiply this with differential output, what you will get is a 2 by pi Gm into RL, because you have a load RL, cos where omega RF is multiplied with omega LO, cos omega RF minus omega LO pi, because it is by 2, this 4 by pi is converted into 2 by pi. So, plus cos omega RF plus omega LO t, you if you consider 3 omega LO, it is a 3 omega F and it has a multiple component, but we consider it as a filtered out. So, you will get a cos omega RF minus omega LOT, and if you filtered out this as well, your conversion gain. So, this is a active mixer gain, and we should write it as a conversion gain, which is given by 2 by pi Gm into RL, and that we have already seen in the previous cases also, which is a 2 by pi Gm into RL, or for Gilbert cell also it is the same. And your IIP3, as we have discussed in the while discussing the low noise amplifier, it is a proportional to the overdrive voltage of the input stage. Now, the single balance mixer, it is the same we have drawn. So, IDC plus IRF, it is replaced with the BJ MOSFET, and that is a MRF MOSFET, and this is the same configuration. It is a single ended input, because here the input is a single ended, that is why it is called a single balance. The LO is a differential, it is the differential output, and that RF transistor provide, and gain is a 2 by pi Gm into RL. It has a disadvantage that because there is a single means ended input, so there is a high LO to RF, LO to IF or RF to IF fed through, but the advantage is it consumes a low power and it has a single ended input, you do not need to convert into the differential. So, in many cases this mixer is widely used where there is a constraint in terms of the power, and you have a advantage in this case, you do not have a multiple stage transistor. So, you can have a better linearity as well. So, this is about the single balance mixer. Single balance mixer operation, this is already we have discussed, and one more thing I want to add is a noise and interference. So, in a single balance, any noise or interference at the LO port appears at the output, making it important to consider potential noise source. And linearity and IP3 of active mixer. So, as I told, it is proportional to overdrive voltage. In this context, the load, that is a channel, load channel, if designed properly and especially if it is a resistive, typically does not contribute significantly to nonlinearity. Now, the switching component, the switches used in a mixer also have a limited impact on overall nonlinearity. So, it is a crucial to select the appropriate DC biases for both the output and the LO signal to ensure that switches remain in saturation. These switches must remain into the saturation during the half cycle they are active. Then this helps in isolating the low transconductance device from the mixer output, and this capacitor, which is a CP, it should be minimized. This remain in the constant, and this capacitor here, that should be minimized. Then you will have a better linear output. So, minimizing the parasitic capacitance. The parasitic capacitance at the common source of each switching pair that we have seen in the CP must be minimized, and in modern nanometer CMOS processes this condition is generally met comfortably for most gigahertz RF application. So, your GM by GM 3 and 4, so that is a GM of 3 and 4 by CP should be greater than of, so GM 3 and 4 by CP. So, this here this CP consists of multiple capacitors from the M3, M4 and the M1, and that parasitic CP, if we try to reduce the CP and increase the GM, if it is greater than, it should be much greater than omega. So, we need to minimize the GM 3 by 4 and we should maximize, we should minimize the CP and we should increase the GM 3 comma 4. So, and impact of transconduction stage, the transconductance stage appears to be a critical factor influencing the linearity, and as I told, the O drive voltage should be as high as possible. And what is the challenges in multi-stage mixer? Active mixer usually consists of multiple stages stacked together, which can pose the challenges in maintaining headroom, and that is why your O drive voltage is reducing and preventing unwanted distortion. So, achieving IIP3, despite the challenges, achieving a IIP3 better than 1 volt, or let us say if we consider 10 dBm is possible, and some linearity, some literature reports success in achieving this level of linearity by active mixer operating at supply voltage of 1.2 volt. So, aim is to have the voltage headroom which is a high enough. So, now we will discuss about the more architecture of the mixer and how can we design the mixer by based on the parameters available in the next class. Thank you.